You know, back in the early 20th century, the picture of the atom we had was, well, it was beautiful. A tiny little solar system with electrons orbiting a nucleus like planets around the sun. It's elegant, it makes sense, and it was completely fundamentally wrong. Because see, according to every law of physics they knew, that little solar system should have destroyed itself in less than a second. So the biggest mystery in science wasn't just what the universe is made of, but a much bigger question: why is there a universe at all?
This huge problem had a name: the classical catastrophe. And the logic was honestly inescapable. You've got an electron, a charged particle, right? And it's orbiting the nucleus, which means it's constantly changing direction. It's accelerating. Well, one of the bedrock laws of physics, Maxwell's equations, says that any accelerating charge has to radiate energy. It has to glow. And if it's losing energy, it's slowing down, and it should spiral right into the nucleus in about a trillionth of a second. The fact that you're here, that I'm here, that anything exists, meant that physics as we knew it was broken.
So to figure this out, we're going to follow the incredible story of the Danish physicist Niels Bohr. We'll start with that catastrophe. We'll look at Bohr's totally radical solution and the new rulebook he wrote for the universe. Then we'll see how it perfectly unlocked the atom's secret barcode of light. And finally, we'll uncover the truly beautiful, deeper reason why it all has to be this way. It's going to be a fun ride.
Okay, so let's really set the scene. It's the early 1900s. We've got this planetary model of the atom. It's the best idea anyone has, but it's staring right into the abyss. It just doesn't work. This right here lays it all out. On the left, you've got the logical, undeniable conclusion from classical physics. Atoms radiate, they spiral, they collapse. Matter, as we know it, shouldn't exist. And on the right, well, just look around. Reality. Atoms are incredibly stable. Matter is everywhere. Physics wasn't just off by a little bit. Its fundamental principles were completely failing at the scale of the atom. It needed more than a tweak. It needed a revolution.
And the person who started that revolution was Niels Bohr. Now, in 1913, he didn't just try to patch up the old rules. No, he did something way more radical. He just threw them out and wrote a completely new set. It was an absolutely audacious move.
Bohr's solution was to just propose a whole new set of rules for how atoms work. First, he just declared there are special orbits, we'll call them stationary states, where the old rules about radiation just don't apply. An electron in one of these orbits is perfectly stable, period. Second, he said that an atom only gives off light when an electron makes a quantum leap, jumping from a higher energy orbit down to a lower one. And third, that light isn't a continuous wave, it's shot out as a single, discrete packet of energy, a photon.
And this is the masterstroke. The energy of that little photon that flies away isn't random. It is precisely the difference in energy between the orbit it started in and the orbit it landed in. This one simple, beautiful equation holds the key to understanding the secret language of every element in the universe. Now, this is all brilliant, right? But it begs a massive question. What decides which orbits are the special, allowed ones? There has to be some kind of rule, right? Well, Bohr found it, and it is the engine that makes this entire model work. Bohr figured out that a property called angular momentum, which you can think of as the amount of oomph in its orbit, was quantized. And this idea is absolutely revolutionary. It means that angular momentum can't just be any old value. It comes in discrete, chunky, prepackaged amounts. It's kind of like money. You can have $1 or you can have $2, but you can't have $1.43 as a single piece of currency. Some values are allowed and others are just forbidden.
And this is the rulebook right here. The angular momentum, L, can only be a whole number multiple of a tiny fundamental constant of nature called h bar or h bar. That number, n, is what we now call the principal quantum number. It can be 1 or 2 or 3 and so on, but nothing in between. It's like a cosmic address for each allowed orbit. This one single rule dictates everything else about the atom's structure.
And that brings us to a really common misconception. It's easy to think of the atom as a mini solar system, but it's not quite right. A planet, like Earth, could theoretically orbit a little closer or a little farther from the sun. But for an electron, there's no choice. It gets a pre-approved list of orbits, and it has to be in one of them. The space in between is totally off-limits. So if the orbits are quantized, it makes sense that the energy of those orbits would be quantized too. And when you work through the math from Bohr's rule, you get this stunningly simple formula for the allowed energy levels. The energy depends on that quantum number n, but look really close at that equation. The most important part isn't a letter or a number. It's that little minus sign. What in the world does that mean?
That minus sign is everything. It tells us the electron is bound to the nucleus. Think of it like this. We define zero energy as an electron that's infinitely far away, totally free from the atom. So to be trapped inside the atom, the electron has to have less energy than that. Its energy has to be negative. It's in an energy debt. If you want to free that electron, you have to pay that debt. You have to add energy to get it back to zero. So we have this incredible theoretical idea of these discrete, locked-in energy levels. But how do we know any of it is actually real? Well, this is where the theory smashes into reality, and it's where the Bohr model had its greatest triumph. It explained the mysterious, unique barcode of light that every hydrogen atom gives off. Just look at this. It's amazing. When an electron jumps from the third energy level down to the second, it spits out a photon with a very specific amount of energy, which our eyes happen to see as red light. If it makes a bigger jump, say from the fourth level down to the second, it releases a more energetic photon, which we see as a teal color. An even bigger jump, from 5 down to 2, gives an even higher energy blue-violet photon. And the crazy part? The energies calculated from Bohr's simple formulas match the observed lines for hydrogen perfectly. It was like finding the Rosetta Stone for atoms. Now for years, Bohr's rule about angular momentum just worked. It was amazing, but nobody really knew why it had to be true. It kind of felt like a rule he just pulled out of thin air. The deeper reason, the why, came a decade later from another brilliant mind, Louis de Broglie, and honestly, it's one of the most beautiful ideas in all of physics. So in 1924, de Broglie comes along and asks this totally wild question. What if particles, like our little electron, aren't just tiny specks? What if they are also waves? What if the electron is this sort of wave of probability that's spread out all the way around its orbit? Now just think about that for a second. If the electron is a wave circling the nucleus, for it to be stable, it can't interfere with itself and cancel itself out. So after going all the way around, the wave has to meet up with itself perfectly in phase. It has to create what's called a standing wave, just like a vibrating guitar string. And this creates a very strict condition. The circumference of the orbit must be able to fit a whole number of wavelengths. 1, 2, 3, 100 wavelengths, but not 2.5. That would crash into itself. And here is the absolute magic. This simple geometric rule that a whole number of wavelengths has to fit into the circle is all you need. When you take this idea and you plug in de Broglie's formula for the electron's wavelength, you do a little algebra and something incredible happens. Out pops exactly Bohr's original seemingly random rule for the quantization of angular momentum. And this is the deep, profound insight. Quantization, this weird quantum rule, isn't some arbitrary law that was handed down from on high. It is the natural, inevitable consequence of a wave being confined to a certain space. All the weirdness of the atom just emerges from the simple, elegant geometry of a wave fitting neatly into its container. The why was geometry all along. Now, for all of its incredible, mind-blowing success, the Bohr model wasn't the final chapter. It was an absolutely critical first step, a brilliant sketch of the atom, but a more complete and frankly weirder picture was still to come. I mean, you can't overstate the successes. It solved the stability problem, it perfectly predicted the hydrogen spectrum, it was amazing. But it had some big failures. It completely breaks down for any atom with more than one electron. Things just get too complicated. And we now know it gets some details wrong even for hydrogen. For example, it predicts the lowest energy state should have 1 unit of angular momentum, but the full theory of quantum mechanics shows it actually has 0. So it was a glorious and vital stepping stone, but not the final destination. So let's end on a kind of a mind-bending thought here. The math that describes the electron in an atom is all based on an inverse square force law. You know what else is an inverse square force? Gravity. So what if you had a gravitational atom? Let's say 2 neutrons orbiting each other, held together only by gravity. Well, the math would look identical. You would get quantized gravitational orbits, discrete gravitational energy levels. Now, the energies would be ridiculously, impossibly tiny, but the principle is the same. And it shows that Bohr's core insight, that waves confined by a force lead to quantization, isn't just a weird rule for atoms. It's a fundamental principle of nature, woven into the very fabric of waves and space itself.